All right, let's move on to our main topic for today. And that is, again, numerical integration. And let's take the homework problem that you had for today as our example. Okay. You may have just mimicked my code, just copied and pasted and made appropriate changes, which is fine. But I do want you to understand what's going on. So the function you were integrating in number 12 is the function f of x equals square root of x to the fifth minus 200, kind of a strange function. Does it have any applications? None come to mind. However, if I had a plus sign there instead of a minus sign, it could be related to speed along a parametric curve. Because of the square root, the formula for that speed was square root of f prime of t squared plus g prime of t squared. So if there were a plus sign in there, definitely I could come up with an application of this. The minus sign is not so clear. Enter the function. Let's try to get an approximate feel for the answer by making a plot. We're trying to integrate this thing, what was it, from 4 to 12? So let's plot this where x goes from 4 to 12. There's our plot. And we can just try to eyeball the area under the curve. Now the graph doesn't go down to the horizontal axis here, exactly, but close. If I draw a line here from this point over to this point and imagine a triangle with base going from 4 to 12 and height going from 0 to 500 or so, that would give me a triangle whose area is probably too big. In the ballpark though, the base would be 12 minus 4 would be 8, and the height would be 500. Let's see, 1/2 times 8 times 500 be about 2,000. The area under this curve is going to be less than 2,000, but maybe not too far. In fact, if you remember, you should have gotten about 1666.88. Did you get that? That was the best approximation to 2 decimal places. Can Mathematica confirm that that's the answer? Yes. Although if you do this, use the palette to get a definite integral on there and enter it. I don't know if you did this or not, probably not. The answer looks pretty weird. Yeah. What in the world is that? That's just a way of representing the answer exactly involving something called the hypergeometric 2f1 function. What in the world is that? Don't worry about it. Okay. I actually did use this function once in a research paper that I wrote. It came up in a model for actuarial science, actually, in kind of a crazy way. But it is kind of a crazy function. Instead, we just want a numerical approximation. You can do a / capital N at the end. This seems to involve a problem as well, though. You involve the imaginary unit I, What's going on there? Well, again, this is a situation where Mathematica is making things more complicated than it needs to. Do notice that that coefficient of I is very close to 0. Effectively, that's numerical error. I think if we do RE of this, that means take the real part, it gets rid of the I. Yeah. RE stands for real part. You can also get more decimal places here, which might be of interest. If I do this integral in here and put the capital N at the front and put, say, a comma 10, then I get 10 significant digits. Yep. For the answer. If I want 20 significant digits, I can do this. Okay. So the capital N does the approximation, whether you do a / at the end or at the beginning by putting the thing you're trying to approximate inside square brackets. If you put a comma 20, you can get 20 significant digits. Again, the RE here just got rid of the I. It's not a big deal. Yeah, and that does approximate to 1666.88. I didn't expect you to do what I just did here. What I wanted you to do is I wanted you to use the summations. So again, our interval goes from A starts at 4 and goes up to B equals 12. That's the interval of integration. So start by saying what A is and what B is. The semicolons technically suppress output, but I kind of just like using those to separate equations. The left-hand sum is a function of n. Everything does depend on n, the number of subintervals, which means the same thing as the number of rectangles. And you just need to go over to your palette, like the writing assistant here. Make sure you've opened the typesetting menu. And the summation symbol's down there. Just click that. Let I go from 0 to n minus 1. You just got to tab over to these different boxes. The function I've already given a name to, it's called f. Just type the f in there. Just make sure, yeah, it is the right function. Okay. Just was wanting to make sure it didn't interfere with the previous thing that I did with the parametric curve. And remember, in your mind, we're adding up areas of rectangles. Area of a rectangle is base times height. The base is the width of each interval. If t is the variable, we call it delta t. If x is the variable, we call it delta x. But in terms of a and b, it's b minus a over n. That's delta x in this case. That's the width, the base of each rectangle along the bottom. When I plug numbers into the function, that determines the heights of the rectangles. What number do I plug in to the function? When I wrote it by hand, I wrote t sub I when the variable is t, or x sub I when the variable is x, equals a plus I times delta x. So effectively, I'm typing a plus I times delta x in there. Delta x is b minus a over n. That's what I'm typing inside the f. A plus I times delta x is b minus a over n. There's your left-hand sum. Do a semicolon to separate that function from the right-hand sum. You can copy and paste. Change the word left to right. Don't forget to do that. Change the 0 to a 1. Change the n minus 1 to an n. And that'll be a right-hand sum. For the trapezoid sum, you don't need a summation. You can just average the left and the right-hand sums, add them up, divide by 2. Once again, I emphasize, notice that when you define these functions of n in this case, you need the underscores, but once they're defined, you do not need them. Before we use these, let's make a prediction about whether they're going to be too big or too small. So we saw the graph of this function looked like this. Remember, the idea of a left-hand sum is that for each subinterval, like the first one here, you take the left endpoint and go up to the graph to determine the height of the approximating rectangle. So the rectangle is going to look like this. Do the same thing for the second subinterval, go to its left endpoint, go up to the graph, and make a rectangle like this. Do it for the third, etc. Adding up the areas of those is going to give you left of n. So when I draw left of n here, I mean left of n is going to be the sum of the areas of those rectangles. You can see they're under the curve because the curve is going up. The left-hand sum is going to be too small. On the flip side, the right-hand sum is going to be too big. Once again, draw the subintervals. For each subinterval, go to the right-hand endpoint to determine the height of the rectangle. Go up to the graph and over, backwards like that. And you can see these rectangles are going to have an area too big. Keep going, etc. The sum of those areas is right of n. So when the function is increasing, the left-hand sum is going to be too small and the right-hand sum is going to be too big. The function we're decreasing, it reverses. For a decreasing function, the left-hand sum is too big, the right-hand sum is too small. How about the trapezoid rule? I picture a bit bigger here. What happens with the trapezoid rule? It's the average of the left and right-hand sums. That can be interpreted in terms of areas of trapezoids. What are trapezoids? Well, one way to make a trapezoid is it's a rectangle with the top of it slanted. That's an example of a trapezoid. And that's the kind we get here. And how do we get them? For each endpoint, draw a dot on the curve. And then the trapezoids that approximate the area under the curve are formed by connecting the dots for the tops of the trapezoid. So the first trapezoid looks like this. The second trapezoid looks like this. The third one looks like this. The fourth one looks like this, etc. Because the graph is concave up, those line segments are above the graph. So the trapezoid rule is going to be too big. The sum of those areas is trap n. And because the graph is concave up, those lines connecting the dots are going to be above the graph. And the area under them is going to be too big. We're trying to find the area under the green curve. We're approximating it with areas of trapezoids. They're above the curve, so the area is too big. The approximation is too big. If the graph were concave down, though, then the approximation would be too small. If the graph were concave down, then the tops of the trapezoids are going to be below the curve. These are facts that are in the reading in section 7.5 that you should know for exam 1 and 2 weeks. I highly recommend doing the reading over the weekend. I hope you did. Whether you did or not, it's probably good worthwhile to read it again. We will talk about it more in class on Wednesday. We'll also start talking about some applications, a new kind of application that I will hint at the end of class today. It's worthwhile to do the reading. Something new today is we need to talk about the idea of the error in an approximation. Error in an approximation so you've got a situation, this is the definition. You got a situation where there's some quantity like an integral that you're trying to approximate, estimate. For example, using some numerical method. There is some exact answer, which in most practical situations, you wouldn't know what the exact answer is. And there's some approximate answer. Let's label the exact answer as the actual value. And let's label the approximation as the approximated value. The error in the approximation is defined to be the actual value minus the approximate value. And I try to remember it like that because it's got the benefit that actual comes before approximate in alphabetical order in a dictionary. So that's the way that I remember it. And if you think about this carefully, it is a little confusing because what it means is if the approximation is too small, if it's below the actual value, that actually corresponds to a positive error. Whereas if the approximation is too big, if the approximate value is bigger than the actual value, this corresponds to a negative error. That seems a little contradictory. Too small is a positive error, too big is a negative error, but that is actually the best way to go about doing it. There are good reasons why that makes sense. This does turn out to be equivalent to another equation found by adding the approximate value to both sides. You could say the actual value is the approximate value plus the error, is another way to think about the exact same equation. It is worthwhile, especially today, to keep track of when your error is positive and negative. So what I'm about to do is I'm about to show you calculations of this error for the homework problem in Mathematica. We'll start with n equal to 2. And then we'll also look at what happens with the midpoint rule and Simpson's rule and the error in those, and see how much better Simpson's rule does. And even more importantly, we're going to think about what happens as we increase the value of n. This would be another example of experimentation in math and making conjectures. So let's label the more exact value here of the integral. How about, let's just call it actual value. Equals that quantity there. Actually, that's a little bit of a lie, you might say, because even that's an approximation. But we'll go ahead and call it an actual value anyway. So the error for each of these rules can be found as well as actual minus approximate. Now, I didn't do this in the first class, but I think I'll go ahead and do it here. Let me go ahead and define these to be functions of n. Error left of n is actual value minus the left value. That's the approximation. That'll compute the error in the left-hand rule. For the right-hand rule, change the word left to right here and here. For the trapezoid rule, change the word left to trap here and here. So these are going to define functions that give me the errors for different values of n. Let's see what happens when n equals 2. Let me actually look at the actual approximations themselves first. And to approximate all these to a certain number of decimal places, I'll use the capital N as well. You could have just done a / capital N at the end. I'm going to go ahead and put, let's just say 10 significant digits in here. Not too many. Not 20. What should these numbers, what are they approximating? They're approximating the actual value. The actual value is 1666.88. N is not very big here, so they're not going to be very close. There they are. The left-hand rule is too small. The right-hand rule is too big. The trapezoid rule is a lot closer, but a bit too big. Right? That's what we predicted. The left-hand rule is going to be too small. The right-hand rule is going to be too big. Trapezoid rule is going to be a bit too big. Left and right. Left was too small. Right was too big because the function's increasing. Trapezoid rule is too big because the function is concave up. Sometimes I give exam questions related to this where I do want brief explanations with pictures like this. Why does the trapezoid rule give you an approximation that's too big if the graph is concave up? Draw a picture and give a brief explanation. Say the trapezoid rule is approximating the area under the curve with the areas of the trapezoids, and you can see they're above the graph because the graph's concave up. That's the level of explanation I'm looking for. What about those errors? Add the word error in here. Well, remember, when the approximation is too small, actual minus approximate, it's going to be positive. You're going to get a positive error for the left-hand rule, a negative error for the right-hand rule, because the approximation is too big. Actual minus approximate is going to be negative. And a negative error for this one. This is slightly too big. I shouldn't say slightly. It's still off by 109.66. But a lot better than the other ones. They're off by closer to 1,000. So these errors are pretty big in absolute value because n is so small. Watch what happens as we experiment now and increase the value then. Let's keep doubling it. So instead of 2, let's use 4. I'm just looking at the errors now, not the actual estimations, not the approximations themselves. They will, if I increase n, these will get closer to 1666.88. But I'm just looking at the errors now. So these errors were in the ballpark of 1,000 when you take their absolute values. This error in absolute value is in the ballpark of 100. If I double n from 2 to 4, what happens? Errors that were in the ballpark of 1,000 in absolute value become in the ballpark of 500 in absolute value, very roughly speaking. The error that was in the ballpark of 100 in absolute value gets closer to the ballpark of 25 in absolute value. I doubled n from 2 to 4. These errors went down by about a factor of 2. They got multiplied by approximately 1/2. And this error went down by about a factor of 4. It got multiplied by approximately 1/4. Will that happen again if I double n again? From 4 to 8? Let's see. Yeah, it did. These numbers are approximately 1/2 these numbers. Approximately, not exact. And this number is approximately 1/4 of this number. Let's try it again. Double n from 8 to 16. It happened again. These two numbers are approximately 1/2 these two numbers. And this number is approximately 1/4 of this. 6.8 exactly divided by 4 is exactly 1.7. We have the makings of a conjecture here. If we double n, the approximate errors for the left and right hand rules get cut in half. Twice as close to 0. Though one's positive, one's negative. And the approximate errors for the trapezoid rule gets cut by 1/4. 2 squared is 4. I wonder if that is a relationship that might hold in general. Let's test it out. Instead of doubling it, why don't I try multiplying it by 10? Increase n from 16 to 160. What should happen if my conjecture holds true?
Should get like 11. Should get 11 and 12 and then almost 0.
Yep. If you multiply n by 10, so it goes from 16 to 160, instead of getting cut in half because we multiplied by 2, we should get cut by a factor of 10 for the left and right hand rules. They should go from these numbers to around 11 or 12. One's still positive, one's still negative. And this one, instead of getting cut by a factor of 2 squared, should get cut by a factor of 10 squared. 100 times smaller. So the decimal point should move to the left 2 spots. 0.017 maybe. negative 0.017. Let's see what happens. Yeah, it did. Yeah, and these are 11 or 12 or so. The conjecture seems to be working. And in fact, that's true. Now let me write down a general rough statement that you should know for the exam of what's going on here. If n, the number of subintervals, which represents the number of rectangles and trapezoids for the trapezoid rule, is increased by a certain factor, let's call the factor r. For our examples, r was 2 and then it was 10. We doubled a few times and then we multiplied by a factor of 10. So n is increasing from n, whatever the n was, to r times n. If n is 16 and r is 10, then n is increasing from 16 to 160. Then the error in the left and right hand rules, let me call this, I'll go ahead and just use subscripts, error sub left and error sub right, go down, quote unquote, in absolute value. Technically speaking, when a negative number gets closer to 0, it's actually going up, right? If a negative number gets closer to 0, that's technically increasing. But I'm saying down in absolute value by the same factor, by a factor of r. So effectively, the errors get multiplied by 1 over r. They get divided by r, approximately. And the error in the trapezoid rule, error sub trap, goes down, quote unquote, in absolute value by a factor of r squared. Approximately. That's what we saw. So this is a conjecture. It's not really a theorem because it's not a precise statement that could be rigorously proved. It's an approximation in a mathematical situation that we have confirmed experimentally, you might say. Though only for one example. If you're going to confirm it more widely, you want to come up with lots of other examples and see if it still seems to hold. But even then, it's still just an approximation. It's really more of a rule of thumb. So it's not a precise statement of fact. It's a useful rule of thumb. Can you write down theorems in this kind of situation? You can, but they're kind of technical. And we're pretty much fine with just these approximations. Something else to notice in looking at the errors is that especially as n gets larger, it wasn't so true when n was small, looking at the left and right hand rule errors. But as n gets larger, like down here, when n is 160, the error in the left and right hand rules have the opposite signs, but in absolute value, they're pretty close. They're close to the same distance to 0. And that's why the trapezoid rule gives you a much better approximation. The errors in the left and right hand rules are close to the same absolute value, but they do have opposite signs. Therefore, if I average the left and right hand rules, it should be a pretty small error, and it is. That's a much smaller error in absolute value than these two. Many, many orders of magnitude. In the ballpark of 1,000, better. What about the midpoint rule? Let's go back up here. For the midpoint rule, I told you last Friday to copy and paste the right-hand rules formula. Put that down here. Change the word right to mid for midpoint rule. And then you do need to change what goes into the function. Delta x is still the same. It's still b minus a over n. But we need to change what goes into the function. On each little subinterval, the idea is if this is the left endpoint, call it x sub I minus 1, and this is the right endpoint, call it x sub I. We want the midpoint of that subinterval to determine the height of the approximating rectangle. Use the midpoint to go up to the graph to find the height. What is that midpoint? It's the average of the left and right hand endpoints. X sub I minus 1 plus xi over 2. Well, remember what xi was. Xi, I wrote down, was a plus I times delta x. A plus I times b minus a over n. X sub I minus 1 would be the same exact thing, except using I minus 1 instead of an I. A plus, in parentheses, I minus 1 times b minus a over n. So effectively, it's those two things that need to go into Mathematica and be added and divided by 2. That's what I showed you last Friday. So I'm going to take this thing, I'm going to put it in a fraction, put a 2 in the bottom of it. This thing in parentheses here, this is going to be my x sub I, and then put a plus sign in front of it and paste it here as well. Oops, not that. I don't know what happened there. Okay, let me try that again. Here's my fraction. For extra clarity, I'm putting parentheses around these things. These parentheses that I'm using right now are not absolutely necessary. But if I change this I to an I minus 1, I must have parentheses around it. That has to be there. So this is x sub I minus 1 right there. And this is x sub I. I'm adding them and dividing by 2. This could be simplified. Like the a's could be combined to give you a 2a. The b minus a over n could be distributed through the parentheses there and combined with that. It could be simplified, but it's probably best just to leave it like this. That's entered. That's the midpoint rule. Question?
So another good way of thinking about it, the left-hand rule, that a is increased by half of delta x.
That is another way to think about it, and that's okay. Yep. I should probably do error mid as well. Error mid is the actual value minus mid of n. What's the error in the midpoint rule when n is 160? It's there. It's even smaller, closer to 0 than the error in the trapezoid rule. In fact, it's about twice as close to 0 in absolute value, right? Half of 17 is 8.5. We've got negative 0.017. This is positive 0.0085. It does about twice as good as the trapezoid rule does. And yeah, if you looked at the actual midpoint value when n is 160, it's very close to 1666.88. Very close. Because the midpoint rule is doing about twice as good as the trapezoid rule with the opposite sign to its error, that's why it's good to try a weighted average for Simpson's rule, where you give the midpoint rule twice the weight. Like this. This is called a weighted average. The weight of the trapezoid rule is the 1 that's in front that I didn't type. 1 times the trapezoid. The weight of the mid is the 2. I've got to divide by the sum of the weights. 1 plus 2 is 3. Effectively, it's like I've got a value for the trapezoid rule and the value for the midpoint rule, and I'm averaging 3 numbers. One of the numbers is the trapezoid rule and 2 of the numbers of the midpoint rule. And I'm dividing by 3. Again, the intuition is because the midpoint rule does twice as good as the trapezoid rule does. The error is twice as close to 0 with opposite signs. So it's good to add these. So that's Simpson's rule. What's simp of 160? Let's even do, say, 20 decimal places. It's that, compare it to the true value, actual value. Very, very good. It's matching way out to there. Yeah, 7 places after the decimal, 11 significant digits. Pretty good. It even does a pretty good job even when n is 2. I mean, it's not as good, but it's pretty good. 1666.716. Yeah, that's pretty good for n equals 2. What happens to the error in Simpson's rule? I haven't defined that yet. Error in Simpson's. When n increases from 2 to 4, say, oops, not from 2 to 43. What's happening to that error? So the error is doubling, or excuse me, n is doubling. The error is going from about 0.16 to about 0.016. Seems to be going down by a factor of 10. Actually, it's going down more typically by a factor of 2 to the 4th, 16. If I do increase n by a factor of 10 from 2 to 20, it turns out the error should go down by a factor of 10 to the 4th. The decimal should go to the left by 4 spots, effectively. And I get 4 zeros in there. Now, this is not exactly 10 to the 4th, very roughly, but I do get 4 zeros there. Simpson's rule not only does a lot better for a small value of n, as you increase, its error decreases even faster. Okay. So make sure you do that reading. And continue working on more homework problems from this section, due on Wednesday.